Now see the parameters of half-wave rectifier. From the output of the waveform, from the half-wave rectifier output waveform, I am going to discuss these parameters. Now here, this is the output of your half-wave rectifier. Output of your half-wave rectifier. Now before going to these parameters, see here Im is called your maximum value of the waveform, and here Im is called the maximum value of the waveform, whereas time period for this waveform is 2 pi. Time period for this waveform is 2 pi. What is the time period? Time taken to complete one full cycle. Now here, this is the time taken to complete one full cycle here. After reaching this 2 pi, again the same cycle is repeating. After reaching 4 pi, again the same cycle is repeating. That means 4 pi minus 2 pi, it is 2 pi. 6 pi minus 4 pi, 2 pi. 2 pi minus 0, 2 pi. That means in this case, the time period is 2 pi. The time period for this waveform is 2 pi. Okay. Now by using this, I am going to discuss the average value first. First, I am going to discuss the average value. Now, what is the definition for average value? Already we discussed this average value in our first unit. The definition for the average value is, it is the ratio of area covered by the waveform. Now here, this is the area covered by the waveform. This is the area covered by the waveform to the curve travel. Okay. Once again, I am repeating the definition. Average value is defined as, it is ratio of area covered by the waveform to the curve travel. If you want to determine the area covered, you have to integrate this part with these intervals. That means here 0 to 2 pi IL d omega t. Why? Because the intervals are from 0 to 2 pi. The curve travel is 0 to 2 pi. So that's why it is integration with 0 to 2 pi IL into d omega t. Here this is IL waveform. That's why it is IL into d omega t. By curve travel is 2 pi here. By 2 pi. Okay. But general equation for the sine wave is given by Im sin omega t. So I am replacing this IL with Im sin omega t. Now we can write this equation as 1 by 2 pi integral 0 to 2 pi Im sin omega t. Now split this 0 to 2 pi intervals into two parts. Why? Because in this, one is positive half cycle, one is 0. We have two intervals in this. So that's why you split into 0 to pi as well as pi to 2 pi. Here I written everything here. Between 0 to pi, the waveform is IL is equal to Im sin omega t. Between pi to 2 pi, it is 0 here. Between pi to 2 pi, 0. Why? Because here, this is 0 between pi to 2 pi. Okay, by using this, I am deriving this part. After this part, you are going to get this part here. IDC is equal to, here, average value is nothing but IDC. Now IDC is equal to 1 by 2 pi. Integral of 0 to 2 pi will become 0 to pi. Im sin omega t. What will happen to pi to 2 pi? It is 0. No need to write. So that's why I negate that pi to 2 pi. Because of it is 0. Now integrate this part. Integration of sin theta is minus cos theta. So it is minus cos omega t. Okay. 0 to pi intervals. Last 10 minutes. Okay. Now if you integrate this part and apply these limits, you are going to get Im by pi. Now this is the average value or DC current. Average value or DC current for this waveform. For this waveform, this is your average value. Okay. Similarly, I want to determine the voltage and voltage. That is your current. I want to determine the voltage. Now, what is the voltage equation? V is equal to I into R. General equation for voltage is given by V is equal to nothing but E is equal to I into RL. Now, IDC already we solved in this case here. IDC is equal to Im by pi. I substitute here. Im by pi into RL. Okay. Now, what is the value of this Im? Im is given by ESM by RF plus RL plus RS. This is from the circuit diagram. This is from the circuit diagram. I will show the circuit diagram here. See the circuit diagram. Here. This is the circuit related to half-wave rectifier. Now here here this is your secondary voltage, nothing but voltage rise. Voltage rise is equal to voltage across this part and voltage across this part. I already explained in the case of half-wave rectifier. Okay, now this part plus voltage rise plus voltage drops. Okay, now here I'm assuming there is an internal resistance present in the secondary winding, that is RS. There is an internal resistance present in this secondary winding. I'm assuming that as RS. Okay. Already for the diode, we have the forward resistance, that is RF, and across load resistance, it is RL. Now, by using this RS, RF, RL, I'm going to write the equation. Now, see that equation here. I is equal to V by R here. V by R. So in that case, in the circuit, these all are connected in series. RS, RF, RL, all are connected in series. So that's why it is RF plus RL plus RS. RS is called internal resistance for your secondary winding. RL is load resistance. RF is forward resistance for your diode. Okay. ESM is maximum value of your waveform. Already discussed here. See here. This is maximum value of the current. Similarly, maximum value of the voltage will become ESM. If it is current waveform, IM. If it is voltage waveform, ESM. Okay. Secondary maximum voltage. Okay. I is equal to V by R into pi into RL. Okay. From this, I am writing this equation and just I am substituting IM is equal to ESM by RF plus RL plus RL. Then you are going to get this EDC waveform. Okay. Whereas in this case, RS and RF is very smaller values. Why? Because RS is internal resistance. RF is forward resistance is very less in the case of diode. Already discussed in the case of PN diode. Reverse resistance is in terms of mega ohms. Forward resistance is in terms of kilo ohms. Okay, forward resistance is very less resistance. So that's why we can neglect this RF plus RS here. We can neglect RF and RS. These two are very, very small when compared to RL. So RF plus RS is approximately is equal to RL. Then what will happen to this total equation? RL. Now RL is going to cancel. So here RL, here RL. Both are going to cancel. This total part, this is going to cancel. Then you are going to get ESM by pi like this. EDC is equal to ESM by pi. Okay. Now that is total about your average value of your current as well as voltage waveforms. Now see the RMS value. It is root mean square value. Now here, this is root of 1 by 2 pi into 0 to 2 pi Im sin omega t whole square into d omega t. Okay. Whereas again divide this part into two parts, 0 to pi as well as pi to 2 pi. No need to write pi to 2 pi. Why? Because in this waveform pi to 2 pi is 0. Only 0 to pi is there. Only 0 to pi is there. That is 0 to pi Im sin omega t whole square. The formula is Im sin omega t whole square. So that's why it is Im square sin square omega t into d omega t. Okay. Now integrate this part with respect to omega t. Before integrate, write this equation in terms of cos. 1 minus cos 2 omega 2 by 2 by using mathematical equation. Okay. 1 minus cos 2 omega t by 2. Okay. Now integrate this part and apply this limits. Then you are going to get the result as IRMS is equal to Im by 2 only. See here, 1 by 2 constant is omega t by 2. Integration cos theta, it is sin theta. Just apply the limits 0 to pi. Upper limit minus lower limit. Then you are going to get Im by 2 RMS value for your half-wave rectifier. Okay. Similarly, this is current and if you want voltage, again V is equal to I into R. I means already we got Im by 2. Substitute here Im by 2. Okay. Now it is Im into RL by 2. Again substitute Im is equal to ESM by RF plus RL plus RS. Already discussed this topic. Here I discussed now. Here. Okay. So that value is ESM by pi into RF plus RL plus RS. Again this total RL and this RL is going to cancel. Similar to previous case and it will become ESM by 2. EL is equal to ESM by 2. This concept is similar to this concept. Okay, just substitute Im is equal to this part. Then cancel this RL and this RL. You are going to get ESM by 2. Okay, this is your RMS value. And after DC power, equation for power is EDC into IDC. I can write this EDC as IDC into RL. V is equal to I into R. It will become I into R. Okay, now it is I square into RL. Here, I square means Im by pi. IDC. What if we will get IDC? Previously, I got IDC as Im by pi. In previous case, I got IDC as Im by pi. Just I'm going to substitute here. Im by pi whole square into RL. Okay. Now instead of Im, again substitute ESM by RF plus RL plus RS. Now this is the equation for output power, ESM square RL by pi square into RF plus RL plus RS whole square. Okay. This is PDC. Similarly, I want AC power. AC power means transformer secondary winding. So it is IRMS square into what are the resistance present in the case of transfer, in the case of half-wave rectifier, it is RF plus RL plus RS. Okay, so it is I square into R. Sorry, this equation is wrong. It is I square into R. And the formula for power is I square into R. P is equal to V into I. From that, I square into R. Here, I square into R. I square into RF plus RL plus RS. Okay, now we are going to get this equation. Substitute this IRMS is called Im by 2. Then you are going to get this equation. Okay. Now this is PAC and we got PDC here. Substitute this PDC and PAC in the efficiency formula. PDC by PAC. Substitute these two values. Then you are going to get the efficiency as 0.406 by this value. Okay. Now we can neglect this value. RF plus RS is very, very small. So this total part will become neglect. That means denominator is going to negligible value. Then this total value will become 0.406. So that's why the efficiency in the case of half-wave rectifier is only 40.6, and the efficiency in the case of half-wave rectifier is only 40.6. This is your half-wave rectifier parameters.